H2SO4?
Aqueous.
CaSO4.
Aqueous.
Solid.
You got solid, aqueous?
Yes.
Well, which is it, solid or aqueous?
I thought it was aqueous.
You thought it was aqueous because most sulfates are soluble, so that's correct. You would think it's soluble unless it's one of the exceptions. So sulfates are soluble except for silver, lead, mercury, calcium. There you go. Calcium, strontium, barium. Calcium is an exception. So most are soluble except this one here is not soluble. And then water is a liquid, CO2 is a gas. We know those. Okay, so then what did you get for your ionic equation?
Ca2 plus.
Ca2 plus?
Yes. Plus CO3 2 minus.
CO3 2 minus.
Plus H plus.
Plus H plus.
Plus HSO4.
Plus HSO4
Minus.
minus.
Is Ca2 plus.
Ca2 plus.
Plus SO4 2 minus.
SO4 2 minus.
Plus H2O plus CO2.
H2O plus CO2. All right, what did you get for the state for Ca2 plus?
And an ion at solid.
Solid.
Yeah.
CO3 2 minus.
Solid.
H plus.
Aqueous.
HSO4 minus.
Aqueous.
Ca2 plus.
Solid.
SO4 2 minus.
It would be solid.
Is that what the other guys got? What did you guys get?
I wrote for the IE, I just wrote for the other end is CaSO4.
Okay, so instead of this, you wrote CaSO4,
Yes.
like this. And then what state did you write?
Solid.
Solid. Okay. Did anybody else get something different? Calcium carbonate. What did you write for the CaCO3? Solid. All right. So it boils down to what do we ionize? Do we ionize insoluble salts? No. We only ionize soluble salts. And so that's correct. We shouldn't have ionized this because it's an insoluble rather than a soluble salt. And calcium sulfate, if it were aqueous, we would have ionized it, but since it's solid, we don't. So let's correct that here. So it should be like this. But this is very good. You know, I think about 30 to 40% of the class would have ionized this differently. About 30 to 40% of the class ionizes H2SO4 into what?
H2SO4.
2H plus and a SO4 2 minus. But this is not really correct. Because what we're looking at is we're looking at sulfuric acid and water. Water is strong enough to pluck the hydrogen off H2SO4, but is it strong enough to pluck the hydrogen off HSO4 minus completely? No, because HSO4 minus is what we call a strong acid or a weak acid, HSO4 minus, weak acid. And so this is why we do not write this 2H pluses plus a sulfate. But these are very common things I see. Common things I see is calcium sulfate is aqueous because solubility rule. Solubility rules are a bit of a pain to memorize, but it's helpful to know them. All right, so this was your CE, this is your IE. What was your NIE?
Would you like me to tell you the corrected one or what?
Yeah, the corrected one.
Okay. CaCO3.
Okay,
H plus.
okay,
HSO4 minus.
okay,
CaSO4
okay.
plus H2O plus CO2.
Yeah, so it's the same. You got the same. I probably should rewrite this, but I'm not going to rewrite it. In your lab notebook, whenever you make a mistake, this is why you do things in the lab notebook. You don't do things on the final report, because if you start making mistakes like this on your final report, it doesn't leave a good impression. Oftentimes with the final report, you know, neatness counts, I guess, for the final report. So this is why you try to leave the report sheets clean. You want to make your mistakes in your own personal notebook, lab notebook, not on the report sheets. So if you're submitting a report for, you know, a grant, to try to get some money to fund your research, you don't want to have a really sloppy looking report with a whole bunch of scribbles and erasures and whiteout and whatnot. And try to keep it nice and neat. What are you missing? I asked you for something else. Driving force.
Driving force, right.
So what is the driving force? Okay, now this is precipitation. Precipitation is very tricky here. Why? Because we start with a precipitate. And so precipitation isn't necessarily a driving force in this one. And so what I'm going to do is I'm going to put a precipitation with a question mark. Because we're destroying one precipitate for another. And so what this is this is precipitate versus precipitate. Versus precipitate. And so this is different. In Chem 4 you'd never have this. Because in Chem 4 you'd take a solution plus a solution always end up with a precipitate. But this is a new twist. This new twist is because you're now in Chem 1A versus Intro Chem. So you should be able to handle a more difficult situation. This more difficult situation is precipitate versus precipitate. Which one is going to win? That is, the whole thing about driving force is going from something less stable to something that's more stable. So which of these two precipitates is more stable? Sometimes we could figure that out, you know. Sometimes it's not so easy. I mean, this is a +2, that's a -2. This is a +2, that's a -2. And then what dictates how strong it is how it packs together. How it packs together depends on the shape of the anion. Like carbonate is a trigonal planar anion, whereas sulfate is a tetrahedral. So that could play a role. And also the size, the smaller the size. And so it depends on carbonate versus sulfate, which can pack in tighter, get closer. You know. We don't know. So some of the things that we can do is things like, if we had access, we could look at, well, solubility. Not, we know that both of these are insoluble, but they're not 100% insoluble. And so that's probably the best thing. But where can we look for the actual solubility? You know, you memorize the solubility rules, but those are very black and white. So both of these are insoluble solids, but they aren't equally insoluble. You know, which one is less soluble? Which one prefers to be the precipitate more? And so where can I find that information?
The CCS.
Close.
Yes,
It's not CCS. CCS. You know, I just saw something about CCS. You know the acronym? At UCSB, people know the acronym because at UCSB there's this. Have you ever heard of the CCS? The CCS at UCSB is called the College of Creative Studies. The College of Creative Studies is like their honors college at UCSB, so a lot of people want to be in the College of Creative Studies there. But it's not the College of Creative Studies. That's only acronym I can think of. What else do you think of for CCS? Oh yeah, clear colorless solution. That's a very common one, CCS. That's the other place I've heard of CCS. But it's not applicable here because these are going to be both cloudy. Calcium carbonate's white, also called limestone, also called calcite, also just called calcium carbonate. Calcium sulfate is also white. And it's not the CCS, it's the CRC. And what does CRC stand for? This is something I never forgot, you know, because the first time I was told about this CRC was in like Chem 4. In high school they never said CRC. But I never forgot it because it was always so weird. It's such a weird name. CRC stands for chemical, not reaction. Not repository. Although that
Repository compendium.
both, that sounds like it would be repository of information. Anybody remember? Maybe I didn't say. Well, I'm sure I said it because it's CRC. This is the way I remember the CRC.
Consumed for college.
I guess CRC is not so popular anymore. CRC handbook, I should put that in.
CRC insurance. Chemistry.
I actually have this edition,
The 60th edition.
the 58th, I think this is, the green one. Oh, this burgundy one looks nice. 84th edition. It doesn't matter. You don't need to know what the CRC stands for, but it stands for the Chemical Rubber Company. Chemical Rubber Company.
I was going to say chemical organic composition.
So what were we looking for?
We're looking for solubility.
Solubility, right. Which one is less soluble?
Calcite.
Calcite or calcium sulfate?
I'm guessing calcite.
Okay,
I'm not willing to put money on it, but I'm guessing
I'm
calcite.
not gonna put money on it, then it's not interestingly.
I have $1.
Okay,
A couple of cents for lunch.
that's pretty good. Oh, yeah. Except the CRC costs money, so you know what I'm gonna do? I'm just gonna look it up on Wikipedia.
What are you, my elementary bully? Taking money back.
So what dictates, what dictates is how these pack together. You can see the carbonates are trigonal planar, and these are the carbonates here. Normally we have oxygen is red, carbon, I don't know what they're putting here, this color, dark. And then the calciums are the green ones here. And so it packs together quite nicely there in the crystal lattice.
Sedimentary rock.
All right, so keep this in mind. The solubility is 0.013 grams per liter. It's not very soluble. You can barely get any of it in the liter. Only 100, actually not even 130. This is only 13 milligrams will dissolve in a liter at 25 degrees C. So 13 milligrams in a liter. This is calcium sulfate. You can see how it packs in the lattice here. They're just interconnecting things, so you can just see the relative orientations. This just looks weird. The yellow sulfur here, that's going to have 4 oxygens in this tetrahedral arrangement. The calciums are the greens here. And this lattice looks quite a bit different. This is not normally how they represent lattices here, because these aren't covalent bonds. It looks as if they're covalent bonds bonding the calcium and the sulfates. Other names for calcium sulfate: plaster of Paris, diorite, gypsum.
Solubility in water.
Yeah. 260 milligrams per 100 milliliters. So we have to times this by 10, correct? And so if we multiply by 10, that's 2.6 grams. 2.6 grams in a liter versus 13 milligrams in a liter. Which one is more soluble?
Calcium sulfate. There's more per liter, 4,000 milliliters.
Yeah. So there could have been, things that might have clued us in. One is the carbonate's probably smaller and more compact than sulfate. And since sulfate's bigger, it's going to make weaker interactions, weaker ionic bonds. That could have clued us in. And so if we had to guess, then we might have guessed calcium carbonate because of the smaller size of the carbonate ion versus the sulfate ion. Other than that, you know, it'd be pretty hard. But we didn't have to guess, we just looked it up. And so is precipitation a driving force in here? No, because calcium carbonate's actually a better precipitate than calcium sulfate. So maybe we have no reaction here. In this case, you need more information, or you can kind of guess. But all we need is one driving force. So is there at least one driving force?
Gas formation.
Gas formation. Yeah. And do you recall? We're going to go from stronger acid to weaker acid. So this is gas formation. So you could list that. But we also have stronger acid, H2SO4. And we're going to go to weaker acid. Now, let me ask you, what is the weaker acid? Is the weaker acid H2O or is the weaker acid SO2? So we're going from stronger, or not SO2, CO2. Is the weaker acid H2O or is the weaker acid CO2?
H2O.
H2O?
Yeah, H2O
Okay.
would be both.
H2O?
Yeah.
H2O?
Wait, what were the choices?
Well, it is carbonic acid, but I'm not going to do carbonic. I'm just going to do it here because it should hold here as well. And most of the time you'd be right in saying H2O, but in this case you would be wrong. The weaker acid is not H2O. The weaker acid is CO2, but acids are proton donors, aren't they? And where's CO2? CO2 is not going to take a proton out of the nucleus and donate it. And so how is CO2 an acid? It's a Lewis acid. CO2 is a very common Lewis acid. In fact, they say, have you ever heard of acidosis? Acidosis? Acidosis, your blood has to maintain a pH. The pH of your blood has to be maintained at about 7.3 or something like that. You know? pH 7 is neutral. 7.3 is what we call slightly acidic or slightly basic. pH 7.3. A pH above 7 is basic or acidic?
Acidic. Acidic, it goes to 14.
It goes to 14, but it goes from 0 to 14. 7's right in the middle.
Yes, but
Actually, it goes beyond. It goes, you know, from negative something. It's basic, yeah. What happens is if you don't exhale enough CO2, you know, CO2 is an acid, and that's going to change your blood pH, make it more acidic. If your blood pH gets too acidic, then you'll have acidosis, cause a problem. So I think like hyperventilation or something and other things can change or alter your blood pH. And so the weaker acid is actually CO2. And it's weird because normally we don't think of CO2 as an acid at all, you know, but it is a Lewis acid, and it's a very common Lewis acid. In fact, you know, I should do this as a demo. I forgot to do this as a demo. But if you take pink phenolphthalein means it's basic. It has hydroxide in there. You take a straw and you blow bubbles in it. Do you know what happens? The pink color disappears. And this is why your phenolphthalein only has to last for how long?
15 seconds.
15 seconds. Because what's going to happen is there's CO2 in the air. And the CO2 in the air is going to neutralize the phenolphthalein and convert that back to the acid form of phenolphthalein. And so, in other words, CO2 is a common Lewis acid. So this is a Lewis acid here. And so it's a bit unusual. Or this is the reason why I say carbonic acid. If I say carbonic acid, then it's a lot easier because carbonic acid is a Bronsted acid. So we're going from a stronger acid to weaker acid, carbonic acid, which decomposes into H2O and CO2, but it's still acidic. And it's acidic because of the CO2, because water is pH 7 in this case. And CO2, you know, when it comes to water versus CO2, CO2 is going to be much more acidic. But then again, water is often the weaker acid. In so many cases, water is the weaker acid, and it works out. But in this case, it's different. So this is a metathesis problem, but at the next level. This is a much harder metathesis problem because if you said precipitation, you'd be wrong. Did somebody get number 2? Oh, you got number 2, Tristan? What did you get?
K2CrO4 solid.
K2CrO4 solid.
Plus BaCl2.
BaCl2.
That's
Aqueous. Okay, I'll just leave it blank.
goes to BaCrO4.
BaCrO4
Solid.
solid.
And then 2 KCl's.
Plus 2 KCl's. Okay, did anybody else get something different?
Same thing, but K2CrO4 is on solid.
You put K2CrO4 as what? Aqueous. Okay.
I got that as well.
You got aqueous. Yeah. All. If there's any water present, then will this dissolve? If there's any water present, will this dissolve?
Yeah, that's wrong.
Yeah. Basically, yes. This will dissolve if there's any water present because all potassium salts, all group 1 salts are aqueous. And so here I wouldn't have put this, It could be a solid. I could go ahead and sprinkle some solid potassium chromate in there, but it's going to dissolve right away. Okay, so this is the CE. What did you get for the IE?
2K plus.
2K plus,
Plus CrO4 minus.
CrO4 minus,
2 minus.
2 minus,
Plus Ba2 plus.
plus Ba2 plus,
2Cl minus.
it's 2Cl minus,
Goes to barium chromate solid.
barium chromate solid,
2K plus.
2K plus,
2Cl minus.
2Cl minus. Did everybody get that? You ionize all the soluble salts, that's good. Barium chromate is left alone. Then for the NIE, what did you get?
Barium 2 plus plus chromate ion. Barium chromate.
Okay, that's good. Don't forget the solid all the way down. The aqueous we just omit. What's the driving force for this? Precipitation. So for sure, this will be the driving force. Because unlike this previous problem, we're dealing with aqueous solutions, and we're forming a solid. And so there's no question that precipitation will be the driving force for this. That's good. Number 3, did anybody get number 3? You got number 3? Okay, what did you get, Lily? Iron 3 sulfate? Give me the formula.
Fe2 and then parentheses SO43.
Okay.
Plus 6 ammonia.
Plus 6 ammonia,
Plus 6 water.
plus 6 water,
Goes to 3 ammonium sulfate.
3 ammonium sulfate,
NH42SO4.
NH42SO4,
And 2 iron 3 hydroxide.
2 iron 3 hydroxides. Formula?
FeOH3.
All right, give me the states. For the iron 3 sulfate,
Aqueous.
ammonia,
Aqueous.
water,
Liquid.
ammonium sulfate,
Aqueous.
and iron 3 hydroxide?
Solid.
So, okay. All right, next. Oops. What did you get?
2 iron 3
Okay, 2 iron 3s
and 3 sulfates.
and 3 sulfates. Okay, don't forget the charges on these. Not that you did, but lots of people do forget those.
6 ammonia.
Okay, is there a charge on ammonia?
No.
No. Ammonia and ammonium are 2 different things. So,
And 6 water.
6 waters.
And that goes to 6 ammonium ions.
6 ammonium ions.
And 3 sulfate.
3 sulfates.
And then 2 iron 3 hydroxides.
2 iron 3 hydroxides. Okay, and then the NIE,
2 iron 3
2 iron 3s,
plus 6 ammoniums.
6 ammonias,
Plus 6 waters.
6 waters,
That goes to 6 ammonium ions.
6 ammonium ions,
And 2 iron 3 hydroxides.
2 iron 3 hydroxides. Solids. Sometimes, you know, it's easy, especially with so many ions here, it's easy to make little mistakes. So oftentimes what I'll do is I'll just check it, you know, make sure it's balanced. Atoms, 2 irons, 6 nitrogens, 6 nitrogens, 12 plus 12, 24 hydrogens. 6 times 4 is 24 hydrogens, and 6 oxygens. And that would be 6 oxygens there. And then I check charge balance, plus 6 on the left, plus 6 on the right. So this is balanced, NIE. I could do the same thing with the IE, just make sure it's balanced. So I just do a quick check for balance. Is there a driving force for this?
Dilution of the solid.
Yeah. And so precipitation here, your driving force. Good. How about number 4? Did somebody get number 4? Okay, what did you get for number 4? Chlorine gas,
Plus 2 sodium, or sodium iodide,
2 sodium iodides, NaI,
and that goes to 1 iodine solid,
iodine solid,
and 2 sodium chlorides.
2 sodium chlorides. I'm sorry?
Is iodine one a gas?
Iodine's actually a solid, but you have 2 choices here. One, we could make chlorine water. It's not very soluble, but we can get some to dissolve. And so this is called chlorine water. And so we could go gas or AQ in this particular instance. Since it's mostly gas, we could just leave it as gas. And the iodine, you know, it's insoluble in water because it's nonpolar, but a little bit will dissolve. So we could do solid or aqueous. And so we could have chlorine water, which we used the last time, and we could have iodine water, which we could use last time. So if you wrote aqueous, it would have been all right too, for these particular ones. Okay, and then what? Did I ask for the, I only asked for the CE, NIE, and IE for the metathesis reactions. Is this a metathesis reaction? No. And so I could just show the NIE, but this is not even the NIE, is it? What is the NIE for this particular reaction?
Chlorine gas.
Okay, chlorine gas.
Plus 2 iodine ions, or iodide,
2 iodides.
and that goes to iodine solid, plus 2 chloride ions.
Okay, this would be the NIE for this. All right, what would be the driving force? I could have done the IE, you know, in between here. But I would have done this, you did this based on the pattern, I think. I would have done this based on the chart method. And the chart method would yield this directly. Sodiums would be spectators, sodium ions would be spectators.
I have a question about the chart method.
Mm-hmm.
You see that it's not on the chart. It's technically on the chart if it's on the longer chart, right? Because isn't the chart like really 6 pages long or something?
Yeah, the chart in Appendix D is very long. So if it's not on the chart that I handed out, go to the chart in Appendix D. It's like, I think it's 2.5 or 3 pages long. It's much longer though. What was the driving force for this?
Formation of a solid.
Precipitation of iodine. Now, the reason I organize it, the way I organize it, is because, you know, do all combination reactions have the same driving force? It turns out no. And so this is why I don't like to put combination reactions as a category, because it depends. Is it an acid-base combination, or is it a redox combination? Because we look for different things. So formation of a solid, you might think, okay, yeah, that helps, but it doesn't help enough. You know, so for example, formation of a solid or formation of a gas is great for acid-base, and it's also great for not for redox. It's great for metathesis. But is it good for redox? Well, it helps. If we can form a gas, it's very helpful. So if I take 2 liquid waters, and I'm going to make 2 hydrogens and an O2. And so I'm going to take 2 moles of liquid and replace that with 3 moles of gas. This surely must be a large driving force, right? Why not?
Because you have to use a catalyst.
Well, isn't formation of a gas a driving force? Didn't I say formation of a gas is a driving force? So these are the things you think about when you've gone through it so many times. Day after day, you kind of get bored and you start thinking about, that doesn't quite make sense, right? Certain things don't quite make sense. Here, yeah, I'm forming a lot of gas, so is this driving force? And the answer is no. So that's level 1. You think, okay, that's no because I memorized it. I memorized that. What's the driving force? This is not a metathesis, correct? This is not an acid base. What kind of reaction is this?
Is it the chart method?
Yeah, we could do this via the chart method of skeleton redox. This is a redox reaction. And for redox reaction, I've memorized the driving force. The driving force for redox reaction is more active to less active. More active means stronger oxidizer, stronger reducer to weaker oxidizer, weaker reducer. Well, this is just the opposite. Water is one of the poorest oxidizers, one of the poorest reducers. Hydrogen is the prototypical reducer, and oxygen is the prototypical oxidizer. These are strong. So this is going weak to strong. Is that the direction? No. This is not the direction. All right, number 1, you've memorized it. You've memorized that the driving force for metathesis and acid-base are different than the driving force for redox. That's level 1. So you think, the memorization is no good. But then you go, why? Right? Is you memorize it and then you start thinking, why is that? So can somebody tell me why that is? Why can't I use gas formation as a driving force for redox? And so, you know, yes, you've memorized that basic knowledge, but the next step is not so basic knowledge, right? And so this is the benefit of memorizing things. You memorize it and then you start wondering about stuff. Science is supposed to be this curiosity about things. You know, it's not just you memorize it and leave it at that. Sometimes it is because you just don't have time to wonder why. But can somebody explain why? I mean, this is great. This is a lot of gas, but we don't see it. And it is true that if we do form a gas, it helps. Formation of a gas definitely helps redox. But formation of a gas is minor compared to what? The changes in oxidation state. And so the biggest reason why is because of the, in metathesis, if I have sodium ion, does it change? No, it's just ion combination. So if I have sodium ion on the left, I'm going to have sodium ion on the right in a metathesis reaction. But in a redox reaction, if I have sodium ion on the left, I'm not going to have sodium ion on the right. I'm going to have sodium metal. And these two are totally different levels. One you can eat, the other do you want to eat? No, totally different levels. And so yes, gas formation is great, but it's minor compared to the changes in oxidation state. Changes in oxidation state, our book in Chem 4 calls this Dr. Jekyll and Mr. Hyde. And so it makes a big difference. In metathesis and redox, everything's the same. You're just mixing and matching partners. So you take one ion with one partner and then they switch partners, basically. But in redox, it's a totally different game. And so this is why redox does not follow the same rules that metathesis and acid-base do. And this is why I divide it into these three categories, because they're the rules of the game. Whereas combination can be anything. Combination could be redox, it could be acid-base, it could be metathesis. We have combination with metathesis all the time, like the barium ions like chromate. That's combining barium ions and chromate ions to form barium chromate. Totally different rules. So, so the benefit of doing this is, the sooner you start to memorize these things, or the more time you have to reflect on them and think of them on a deeper level possible. And then hopefully you can catch the challenge problems on the test. Oh, we didn't finish this, did we? So somebody told me precipitation was a driving force. Lots of you will tell me precipitation is a driving force, actually. But, we had a gas over here, so maybe gas formation backwards. And so which one? This is like a seesaw battle, tug-of-war. Which side's more stable, Is it forming the gas side or forming the precipitate side, or neither of these? No, it's neither of those. It's more active to less active, and so we're going to do that. And you should already know this. Which one's a more powerful oxidizer, chlorine or iodine? Chlorine is much more powerful. This is a stronger oxidizer. This is a weaker oxidizer. Now, if we use the activity series, then activity series is based on reducer. And so this must mean iodide is more active. Activity is actually based on either. This is less active. But if you use the activity series, which is the right side of our chart, you would have done this. Lithium's the most active on our activity series. But fluorine's the most active on the opposite spectrum activity series, that is the oxidizer. And so in other words, stronger reducer to weaker reducer. All right, that's good progress. How about number 5? Number 5. Did anybody get number 5 yet? You got number 5? Okay. Let's take a look at number 5. Okay, what did you get for number 5? 2 solid sodiums.
Plus 2 water.
Plus 2 water.
That forms 2
2 sodium
sodium ions.
ions.
Plus 2 hydroxide ions.
2 hydroxide ions.
Plus hydrogen.
Plus hydrogen. Okay, driving force?
Strong oxidizer.
Okay, which one's the oxidizer?
Water.
Stronger oxidizer to Which one's the weaker oxidizer? Sodium ion? Okay. And that must mean that sodium metal is a stronger reducer than hydroxide and hydrogen. Okay. That's correct. That's good. What method did you use to solve this? The chart method? Okay, good. Well, let's see, what time are we out?
12:15.